Okay, everybody. Today we're talking about 2.5 complex zeros and the fundamental theorem of algebra. So where we can get off to the start is, what is the fundamental theorem of algebra? So the fundamental theorem of algebra is a polynomial function of x with degree n, and n has n complex zeros. So we can put n has n complex zeros, which are real and non-real zeros. So now we're talking about, as we mentioned last year, complex zeros can be real numbers and also imaginary numbers. And some of these zeros may be repeated. We also have the linear factorization theorem, where if f of x is a polynomial function of n is greater than 0, then f of x has precisely n linear factors. N linear factors. So what it's saying here is that if it's a polynomial function, we know that regardless of what degree it is, if it's some polynomial with highest degree of 5, we know that there's at least 5 linear factors. Now, we might only have 3 possible zeros that are real numbers, but that means that we have 2 more additional factors that are complex. So this kind of ties back when we were talking about n minus 1 zeros, or excuse me, turning points, and then we said that it has also n at most possible zeros. This is how we can figure out how many real zeros and also complex zeros as well. So the fundamental polynomial connections in the complex case. The following statements about a polynomial function f are equivalent if k is a complex number. So this means that x equals k is a solution, or what we can say also is it's a root of f of x equaling 0. We also could say that k is a 0 of the function f. And lastly, we can also say that x minus k is considered a factor. So is a factor of f of x. And basically all we just said here was the same thing, just written differently. We could say that x equals k is a solution or root of f of x equals 0. K is a 0 of the function f of x, or the function of f, excuse me, and x minus k is a factor of f of x. Now, if we continue on to hear about the complex conjugates of zeros, we can say that suppose f of x is a polynomial function with real coefficients. If a and b are real numbers with b not equaling to 0, and we can say that a plus bi, remember I is the imaginary number, and we can say that I is equal to the square root of -1. So that's something that we mentioned last year. I is equal to the square root of -1. And we can say that a plus bi is a 0 of f of x. Then, if that is true, if a plus bi is a 0, if we get a complex 0 like this, then we can also say that its conjugate, complex conjugate, a minus bi, is also a complex 0. So we can say its conjugate is also a 0. So using that knowledge, we're going to be able to identify other zeros given the information from the problem. So if we go into example number 1, let's first practice multiplying complex conjugates here. If we recall, we said that complex conjugates, so if I have a plus bi times, actually, let's make this a different color so we can see the difference. A minus bi. Yeah, there we go. We got the blue and the red. What this equals out to be is we get, let's see, we get a squared minus b squared. Okay. So a squared minus b squared gives us this whole a plus bi times a minus bi. This is a difference of squares. So because of that, we can get ourselves from here to here. We're going to use that knowledge in multiple examples. So let's make sure we're paying attention for those kind of things. So it's telling us to write the polynomial function in standard form and identify the zeros of the function and the x-intercepts of its graph. So we're told f of x is equal to x plus 2 times x minus I square root of 3 times x plus I square root 3. Well, we want to write it in standard form. All we're going to do is we're going to just FOIL this out. As I mentioned, we can state that this here is a difference of squares. And since it's a difference of squares, we already know that all we need to do is take a squared minus b squared. So we can identify that x is our a. So we put a above the x. And our I square root 3 is considered our b. Now this might be a little hard. Let's see how the camera picks it up. If you can see, let me bring it up a little closer just so you can see. As you can see here, let it focus. I labeled a to be x and b to be I square root 3. So with that, I know that I can write this to be f of x is equal to x plus 2 times the difference of squares. So I'm going to have a squared minus b squared. Well, a and x are essentially the same thing. So I'm going to have some kind of x squared minus, now I just need to take I times the square root of 3 squared. So this is going to be I times I squared times the square root of 3 squared. And we can simplify this again. Well, if we recall, we said I is equal to the square root of -1. And what we also can recall now is that I squared is equal to -1. So with that, we can simplify this a little bit further. We get x plus 2 times x squared minus -1. And then the square root of 3 squared is just 3. And now we're just combining like terms. We're simplifying inside here, not by combining like terms, but by multiplying this through. So we know we're going to get a positive here. And we get x plus 2 times x squared plus 3. And we just need to FOIL out these two binomials together. I multiply the x times the x squared. I get x to the 3rd power. X times 3 gives me plus 3x. 2 times x squared gives me plus 2x squared. 2 times 3 gives me 6. And all that's left is I need to write this in standard form. So I put this from highest degree to lowest degree. So f of x is equal to x to the 3rd power plus 2x squared plus 3x plus 6. All right. Moving on, we can, given this information, we can also even do it when we're given the zero. So it says write a polynomial function of minimum degree in standard form with real coefficients whose zeros include the following. So we have a problem here where we're told that -3, 4, and 2 minus I are zeros of the polynomial function. Immediately, if we see that a complex number is part of the answer, we should know, based off what we just mentioned before, that if we're told that a plus bi or a minus bi, doesn't matter which, either one, if we're told that either one is a 0, its complex conjugate must also be a 0. So that must mean that 2 minus I is a 0, but then also that 2 plus I is a 0. And with that, then we can actually write out our factors. Now remember, these are when we're saying that x equals -3, x equals 4, and x equals 2 minus I, and x equals 2 plus I. In order to write in factor form, so we got to say that f of x is equal to x plus 3, because remember we have to write the opposite, just like how we said in 2.4. And we have to write x minus 4. And then we need to also write out our complex conjugates. I recommend that we put these separately. We're going to try to simplify these as much as possible. So I'm going to write x minus 2 plus I and, or actually I should put a parentheses here, I apologize. So it should be a parentheses here, times x minus 2 minus I. So I've listed out my factors. -3, I put a +3. +4, I put a -4. The 2 minus I, here's my 2 minus I. And the 2 plus I, here's my 2 plus I. Now with when the conjugates, I just write them out. I just write x minus exactly what I have, and it works out pretty nicely. What we have to be careful here with is if we notice that if I group this x minus 2 and this x minus 2 here, I have x minus 2 plus I and x minus 2 minus I. Well, if I call my x minus 2 to be A, and I call these i's to be b's, notice I have an A plus B, A minus B. Huh, that looks a lot like this. A plus B, A minus B. So therefore, this should be some kind of A squared minus B squared. So let's go about and use the difference of squares for this one as well. That means we can say that this becomes x minus 2 squared minus I squared. And we'll keep this left side. Well, actually, we could FOIL this left side out. And after we FOIL it, we get x squared minus x minus 12. So here we got a difference of squares, and then these two, I just FOILed it out. So all that's left is just to simplify even more. Well, we know that I squared is -1. So on top of that, we can FOIL out x minus 2 squared. So let me keep this as x squared minus x minus 12. And I'm going to write this one out to be x squared minus 4x plus 4. And that's essentially from x minus 2 squared, I get this. And then I'm going to have a I squared, which is -1. But then there's also a minus sign here. That gives me a +1. And I have these two multiplying each other. So now I just need to FOIL these two out, or actually combine like terms, and then I'm going to FOIL these two out. So let's write that line one more time. X squared minus x minus 12 times x squared minus 4x plus 5. Now with this, I'm going to multiply these two trinomials together. I get x to the 4th minus 4x to the 3rd power plus 5x squared minus x to the 3rd power plus 4x squared minus 5x minus 12x squared plus 48x minus 60. I noticed that I have some squareds here. I have some cubes, and I have some x's, so I can combine like terms one last time. I'll write my final answer in a different color, so we get f of x equals to x to the 4th minus 5x to the 3rd power minus 3x squared plus 43x minus 60. Now let me just repeat what I did in these last couple steps to make sure that we aren't completely confused on what I did. I'm telling you that when we write these as factors, the complex conjugates will always be some kind of difference of squares. This will happen every single time when we know that we have a complex number as a 0. So I grouped the x and the minus 2 together, left the i's outside, and I realized there's a plus and minus in the middle of them. That's the same thing as an a squared, a plus b, a minus b. I think it's a plus b, a minus b. So this becomes a difference of squares. X minus 2 squared is the same thing as x minus 2 times x minus 2, which FOILed out to be this. I squared was -1, gave me a +1. And x plus 3 times x minus 4 gave me x squared minus x minus 12. I kept that to be the same for the next 3 steps. Once I've combined like terms here, I multiplied these two together, which I just distributed the x squared to all 3 terms, distributed the negative x to all 3 terms, and then distributed the -12 to all 3 terms, which gave me all of these. And then I just combined like terms based on their exponents. I combined the cubes with the cubes, the squares with the squares, the x's with the other x's, and then the negative 60 stayed as negative 60. So with example 3, I'm told that x equals 1 is a 0, but it has a multiplicity of 2. And I'm also told that x equals 1 minus I is a 0. Well, if that's the case, that means that when I have a multiplicity of 2, what we saw before was we can say, okay, that means I have x minus 1 squared, because that's what the multiplicity means, is a 0. Or I can write it as x minus 1 times x minus 1. Either way. But the point being is that's the same. That means x equals 1 is a 0 is happening 2 times. So I need to make sure I have 2 factors of it. This x equals 1 minus I also means that x equals 1 plus I is also a 0. So with that being said, I can write out that f of x is equal to x minus 1 times x minus 1. And I can multiply that, just like how we did in the other example above. I can write it as x minus 1 plus I times x minus 1 minus I. Right, and I group the first 2 numbers together, the x and the 1. And again, I have a difference of squares. So I'm going to be able to FOIL these 2 and then write these as a difference of squares. I get x squared minus 2x plus 1 times x minus 1 squared minus I squared. Every single time we're given a complex number, we should get something like this. We essentially get x minus 1 minus I squared, just like how we got x minus 2 squared minus I squared. Very identical in the process of doing this problem. So we FOIL out the x minus 1 squared and we square the I squared. It simplifies to be x squared minus 2x plus 1 times x squared minus 2x plus 1 plus 1. Because the I squared is negative 1 and another negative makes this a plus 1. At the bottom, combine like terms, I get x squared minus 2x plus 1 times x squared minus 2x plus 2. I FOIL these out, combine like terms, I get f of x is equal to x to the 4th minus 4x to the 3rd plus 7x squared minus 6x plus 2. Now there's a middle step here, and that middle step is, let me just show you over here on the side, is x to the 4th minus 2x to the 3rd plus x squared minus 2x to the 3rd power plus 4x squared minus 2x plus 2x squared minus 4x plus 2. After I combine like terms, I get this answer down below, and this is my final answer. All right, so all we're trying to do here is we're just going to try to write things into standard form of some form of a polynomial. In doing so, you got to make sure you're paying attention to the complex zeros and making sure that you're using the difference of squares correctly. That's really the biggest trick to these problems. And if you're paying attention to that, it's not that bad of a problem. A lot of it's just a lot of multiplying and distributing and then combining like terms. Other than that, you just got to be paying attention to what your exponents are and making sure you're adding and subtracting correctly. So, example 4 says, find all the zeros of f of x equals x to the 5th minus 3x to the 4th minus 5x to the 3rd minus 6x plus 8 and factor f of x over the set of complex numbers. So, here, we're not given any zeros. We need to use what we did in the previous section. We need to make sure that we have our p over q. So remember, p over q is where p is the constant 8 over our lead coefficient 1. So we're going to write out all the factors of 8. That'll be plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. Here, all we're going to do is test out numbers using synthetic division, and if we get 0 as the remainder, we find out that that is a factor. So let's use some factors that I already know that are going to work. I'm going to use 1. So plugging in 1, I got to make sure I'm also checking, are all my x's included from descending order? 5, 4, 3, 2, 1, and 0. So therefore, all numbers are accounted for. I'm going to make sure I put my coefficients. So I have 1, -3, -5, 5, -6, and 8. I have a lot of terms here, so I got to make sure that I also, since I already know ahead of time that this is going to give me a 0, I want to use my remainder as well to find an additional 0. So I bring down the 1. 1 times 1 gives me 1. -3 plus 1 gives me -2. -2 times 1 gives me a -2. -5 plus -2 gives me -7. -7 times 1 gives me a -7. 5 plus -7 gives me a -2. -2 times 1 is going to give me a -2. -6 plus -2 gives me a -8. -8 times 1 gives me -8. And sure enough, I get that 0. So I found out that 1 is a 0. In doing so, we can use these numbers again, the 1, -2, -7, -2, and -8 again, and plug in another value, whether it's 2, -2, 4, -4, 8, -8, or -1. We have to just keep testing them. If I tried out -1, I would find out that I don't get a 0 as a remainder. So then after I've attempted it, I would go, okay, let's try out +2. I try out +2. +2 doesn't result in a 0 either. Now, I'm not showing this on the paper here just because of the interest of space, but that's essentially the thought process that you're doing in these problems. But I know -2 works. So I'm going to show what happens when I do -2. So actually, let me change the color here so we can see the difference. So I'm plugging in -2 into this remainder. So I draw a line, bring down the 1. 1 times -2 gives me -2. -2 plus -2 gives me -4. -4 times -2 gives me +8. -7 plus 8 gives me 1. 1 times -2 gives me a -2. -2 plus -2 gives me -4. -4 times -2 gives me a +8. And sure enough, again, I get another 0. So now I know that 1 and -2 are zeros. And now with that, all I want to do is, I notice that I'm getting really close to a quadratic. Remember, a quadratic would be 3 numbers because it would be the constant x to the first power and then x squared. But since there's still one more, this is some x to the third power. I want to test out at least another number until I get to a point where I get 3 numbers. So let's try out 4. Plug in 4. I bring down the first number. So I get 1 times 4 is 4. 4 plus -4 gives me 0. 0 times 4 gives me 0. 1 plus 0 gives me 1. 1 times 4 gives me 4. -4 plus 4 gives me 0. And now I have found 3 zeros. And then what's really nice is that actually this last line, I got a 0 here. So that means that there's actually no value for x. There's only an x squared and a 1. So using this knowledge, I'm going to make an equation out of it. I know that I can get x squared plus 1, and I can set that equal to 0. And if I subtract 1 to both sides, I get x squared is equal to -1. I square root both sides, and I find out that x is equal to plus or minus I. Remember, the rules of square roots when we're solving for x, we must always include plus or minus. Let me repeat that one more time. When we take the square root of x squared and we're solving for x, we must always include plus or minus. So we get plus or minus I, and we have our other factors. Now, why did I care about the I? Well, because it told me that I need over the set of complex numbers. So that means I need to include real numbers and imaginary numbers. So my final answer here of my factors, or even just listing out the zeros, my zeros are 1, 4, -2, and I get I and -I. And that's my answer. All right. Simple enough. I mean, like I said, the only thing we have to be really careful of is especially here where there's just a lot of multiplication. But this is just doing synthetic division, P over Q, testing out numbers. And if we get zeros, we just keep building it down until we get something with 3 numbers. Once we get to 3 numbers, we've gotten to a quadratic. But if this one was just nice enough that we got a 0 here, so then we just had x squared plus 1, and we set that one equal to 0, and then we solved for x by square rooting and including our plus and minus. And sure enough, remember, the highest degree tells us how many complex zeros we have, regardless if it's a imaginary number or a real number. But in total, we should have 5 zeros. 1, 2, 3, 4, 5. We're good. We've done it correctly. All right. So, looking at example 5, it says the complex number z equals 2i is a zero of a polynomial. Find the remaining zeros of f of x and factor over complex numbers. So we're told that f of x is equal to 2x to the 4th power plus x to the 3rd power minus 7x squared plus 4x minus 60. Well, we know that this 0, z equals 2i, is part of the polynomial. So we know that x equals 2i is a 0, and that must mean that the complex conjugate of this is also a 0. So x equals -2i is also going to be a 0 of this. So because of that, we know that the first step is that we know that x plus 2i is a 0, and x minus 2i is a 0. This is just a difference of squares. Remember, complex conjugates are always difference of squares. If we want to FOIL it, we could, but this simplifies to be x squared plus 4. Since we know that this is part of the 0, we can use x squared plus 4 and do long division with this function here, and we can find out what the remainder is. Using that remainder, we can, or a quotient, excuse me, not remainder, that quotient, we can factor that quotient and find out what other factors are involved. So let's set up some long division. I could put my x squared plus 4 out here, and my 2x to the 4th power plus x to the 3rd power minus 7x squared plus 4x minus 60. We have to always make sure that we have every x included in our long division, just like synthetic division. Likewise, we have to be careful about here that there is no x. So this is really x squared plus 0x plus 4. So we have to be careful with that. We remind ourselves from long division, go, okay, what do I need for this x squared to become a 2x to the 4th? I need a 2, and I need an x squared. I distribute this 2x squared to the x squared plus 4, and I get minus 2x to the 4th. Or sorry, positive 2x to the 4th. I'm going to put a minus on the outside. I need a parentheses there. And the 2x squared plus 4 gives me an 8x squared. I need to distribute the negative through, so I get the minus 2x squared and then minus 8x squared, or sorry, 2x to the 4th and the minus 8x squared. I add them together, and I get x to the 3rd power minus 15x squared plus the 4x that I bring down, and I get this term, these set of terms here. And I need to think about, okay, what do I need to do to x squared to get an x to the 3rd power? Well, I only need another x. So I do plus x, multiply the x through, I get x to the 3rd power, and x times 4 gives me plus 4x. Put a minus sign out here, and I got to make sure that I distribute the minus sign through, so this minus sign becomes a plus. This x cubed becomes a minus. The 4x becomes a negative 4x. I add them up together. I get negative 15x squared because that's just adding to 0. And then the 4x and the negative 4x actually cancel each other out. So I'm just left bringing down the minus 60. And here, I just need to figure out, okay, well, what else do I need to do to get this? Well, I need to also multiply for this x squared to become a negative 15x squared. I just need to multiply by negative 15. Distribute the negative 15 through the x to the x squared and the 4. And nicely enough, we get negative 15x squared minus 60. Gotta put in parentheses, a minus sign on the outside. And then after that, we need to distribute the negative through, so we get a change of sign on all of these. And sure enough, these both cancel out. We get a remainder of 0. With that remainder of 0, we can now realize that this quotient and this factor of x squared plus 4 are factors to this polynomial. And so I now can, so this was my step 2. I put step 1, this is my step 2. Step 3 is to take 2x squared plus x minus 15 equals 0. And maybe I can factor it, maybe not. But I know I can use P over Q. And then once I did P over Q, I can do synthetic division. And negative 3 is a possible 0 that works. So I get 2, 1, and negative 15. And I just do synthetic division here. I bring down the 2. 2 times negative 3 gives me negative 6. 1 plus negative 6 gives me negative 5. Negative 5 times negative 3 gives me positive 15. Sure enough, I get 0 here. And I'm left with 2x minus 5 is equal to 0. Because all I'm left with is 2 coefficients. I add 5. And actually, I'm going to continue the work up here. I get 2x is equal to 5 divided by 2. X equals 5 halves. So if I box what I found that x equals 5 halves is a 0. X equals negative 3 is a 0. And that x equals 2i and x equals negative 2i are all zeros. How do I know if I found enough zeros? Well, my highest degree is 4. I've boxed 4 zeros. So now I know that I'm done here. And it says find the remaining zeros of f of x and factor over the complex numbers. So we just need to write out all the zeros out into factored form. So we know that our final answer is going to be x minus 2i times x plus 2i times x plus 3 times 2x minus 5. And with that, we have found all the factors of this f of x, and f of x has now been factored. We got to make sure that we pay attention to the 2i is the opposite for this negative 2i. This negative 2i is the opposite for this positive 2i. This 3 is the opposite of the negative 3. And then the 2x minus 5, that's just the factor that we were left here. But when we solve for x, we just got to make sure that we write it out that way. Okay? Example number 6. We need to write f of x equals 3x to the third power minus 2x squared plus x minus 2 as a product of linear and irreducible quadratic factors, each with real coefficients that is factor over real numbers. So this sounds like a really crazy problem, but it's really not that bad. It's actually a pretty straightforward problem. What we're going to do here is we're going to do P over Q. And P over Q, we list out our zeros. We got plus or minus 1, plus or minus 2, plus or minus 1/3, and last one is plus or minus 2/3. Remember, P is our negative, is a 2, and our Q is 3. With that, we test out zeros. Well, let's test out the easiest one. We can test out the number 1. So I plug it in 1. And I need to double check again to make sure that all my coefficients are accounted for. 3, 2, 1, 0. Looks good. So I put a 3, -2, 1, and a -2. Doing synthetic division, we bring down the first term. 3 times 1 gives me 3. -2 plus 3 gives me a +1. 1 times 1 gives me 1. 1 plus 1 gives me 2. 2 times 1 gives me 2. -2 plus 2 gives me 0. And what's nice is now that I found out that this tells me that x equal to 1 is a 0. It's a factor. And this gives me a quadratic of 3x squared plus x plus 2. And what we have to determine is, can this be factored? And if we try to look into it, we find out that this does not factor. So we can say that this cannot be factored. Cannot be factored. And since it can't be factored, our final answer that we write down in irreducible quadratic factors is going to be x minus 1 times 3x squared plus x plus 2. And that's our reduced down factored form. Now, that might seem weird because this is still having itself in a quadratic form, but if it doesn't factor, we just got to leave it alone. Do not feel tempted to try to factor something that does not factor. Our last example here is sketching a graph with repeating zeros. Now, this is something we've done before. So this is an example that we did back in, I believe it was 2.3. And essentially, we're just kind of working backwards this time. Now we're just told that something is a 0 and they're multiplicities, and we're just going to do a quick little sketch of it. Now let's look through this and make sure we understand how we do it. So we're sketching the graph of the polynomial function with the given zeros, multiplicities, and sign of leading coefficients. So we're told that -3 is a 0. That must mean that x plus 3 is a factored form of this. And it's a multiplicity of 2, so there's some kind of x plus 3 squared. With that, we're also told that 4 is a 0. That must mean that we have an x minus 4 as a 0. And it has a multiplicity of 3, so there should be a cubed. And we're also told that a is positive. So what that means is that end behavior-wise, once we determine the highest degree, we can figure out where the arrows go. Now, how do we determine highest degree? Well, the HD, highest degree, is just going to be the sum of the exponents. Now, if there's an x on this outside, we need to add up that x as well. But here, that's just these two. So because of that, then we're going to just take 2 plus 3. We find out that the highest degree is 5. That's an odd. And we're told that a is positive. So we know that we're going to get some kind of arrow that goes down to the left and another arrow that goes up to the right. Just like how we've done before. We draw these. This helps us figure it out. So all we need to do now is realize, okay, well, x at -3, x equals -3, I get a 0. So I know that at -3, like I said, we're estimating. -3 is somewhere around there. And at +4, we get a 0. So that's also somewhere maybe over here. So here's -3, here's +4. Let's even write the coordinates on -3, 0. And this is going to be 4, 0. And I mentioned in class, all I care about is if we find some kind of key intercept, whether it's a y-intercept, x-intercept, and then maybe showing the number of turns. Well, our highest degree is 5. We know that there should be some multiple form of turns going on here. And I just want to sketch. So what I'm going to do is maybe find a y-intercept. Now, this might seem kind of weird on how we do it, but if we think logically, if we FOILed all of this out, if we FOILed all this out, x plus 3 times x plus 3 times x minus 4 times x minus 4 times x minus 4. In the end, the constant is just going to be the product of this 3 squared times 4 to the 3rd power. So if I find the y-intercept, which I just make f of 0, that's just going to be 3 squared times negative 4 to the third power. Again, why am I doing this? Because I just want to find the y-intercept. If I FOIL this all out, the last terms of x plus 3 times x plus 3 times x minus 4, blah, 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 continue if I wrote it all out. In the end, the last term is just going to be the product of 3 times 4 times 4 times 4. So that's what I'm doing here. Because all the other terms will have some kind of x. Those get zeroed out because I'm finding the y-intercept. And when I plug this in, I find out that I get 9 times negative 64. And I get f of 0 equal to negative 576. So a really big number. I don't really care about that too much. All I care about is that it's going to give me some number down here in the negative. And now we already can kind of see what kind of graph we're going to have. So this is going to be 0, negative 576. And if we draw this out, we realize that at negative 3 of a multiplicity of 2, so this should bounce, not go through and come up above. So I'm looking for that on your quiz and tests. I'm looking for, are you showing the bounce or are you showing that it crosses? So we know that this bounces, comes back down, goes through the y-intercept, goes back up, and at this 0, it's going to go through. Going to cross, going to connect to our other arrow, and there's our graph. Something very simple, very straightforward. I'm not looking for anything else. I'm just looking, do you have the right end behaviors? Do we have a y-intercept, your x-intercepts based off what we're told? And are you showing that they're bouncing when they're supposed to bounce? And are you showing them cross when they're supposed to cross? You do that, you're going to be perfectly fine on this problem. The hard part is maybe this part. Some people might be like, wait, why did you do that? So let me repeat that one more time. The reason why I did this is because I know that when I multiply out all these factors, and if you don't believe me, go ahead and multiply it. It's going to be a lot of work, but go ahead and multiply it. You're going to see that in the end, if I took 3 squared times negative 4 to the third power, just like how I did here, I get this. This would be the last term if I multiplied every single factor out. So let's do this next one a little bit quicker. I know that negative 1 has a multiplicity of 2. That means I'm going to have an x plus 1 to the second power. And I have a 3 as a 0 with a multiplicity of 2 as well. So that means I have x minus 3 squared. And I'm told that a is less than 0. I said, how do I find what the highest degree is, my HD? I just add these two exponents together. 2 plus 2 gives me 4. I just multiply always my x's together. So if there was an x out here, this would be 1 plus 2 plus 2, but there isn't an x, so we're not going to include that. That must mean that I have them either both going up when my end behaviors or both going down. Well, a is less than 0. That means a is negative. I should have 2 down arrows. Okay, that's helpful. All that's left now is find my y-intercept, and then we can plot our x-intercepts as well. Well, that means I'm going to have some kind of 1 squared times negative 3 squared. Remember, it's this number in here, this 1 to whatever power is out here, negative 3 to whatever power is out here, and we find out that we get f of 0 to be 9. Or excuse me, negative 9. And the reason why it's negative 9 is because we're told that a is negative, so there's also going to be some negative sign out here. So it should be negative on the outside part of here. So negative times the 1 squared times negative 3 squared. This gives us a negative 9. So I apologize, I totally forgot to mention that negative sign there. With that, we can draw our coordinates. We know we're going to have one at negative 1, 0. And we know we're going to have another one at 3, 0. And we know our y-intercept is going to be at 0, negative 9. Now we can clearly see what kind of behavior we have. They're multiplicities of 2, so they should be bouncing here, they're not crossing. So we get a graph that looks something like this. All right. So please make sure if you have questions, put question marks along your notes so that tomorrow in class you can ask these questions. If you have any questions, also just jot them down. I know I went kind of quickly. I'm trying to make sure these videos go a little bit quicker. Today's video was 15 minutes shorter compared to the video before. I'll keep working on it, guys. Let me know what other ways I can improve the videos, and hopefully you guys are enjoying them. I'll see you guys in class tomorrow.